universe, discussing the basic understanding of particle physics and identifying problems and new questions in this field. Join us as we studies of the universe, discover the latest insights from particle physics.
Thank you so much. No, I have a. I think I can be heard, right? You can hear me? Is it on? Yeah, we'll wait. Okay, by the time they fix that, I'm very happy to see such young people, some very young people. But can I just get an idea of how many of you are still in school? Okay, very good. So all of you are have done some course in physics already? So okay, I mean, it's a kind of open-ended lecture. Depending on whether your faces look interested or bored, I'm going to kind of fast forward some things because I didn't know what the audience will be. So I've started at a very general level. So I think, fast forward some of the initial slides, or just for completeness for the young girl here who was so keen on a Saturday morning, I will probably just go over it a little faster. And again, I assume it will be a 1-hour talk. I would like a lot of interaction. I don't have any portions or syllabus to complete. So please feel free to stop me anytime, ask me questions. And if I don't know, I'll say I don't know. If I know, I will answer them. Okay. So yeah. So we can start the first part. It doesn't need these things. It doesn't need slide. Oh, I think the YouTube people will be at a disadvantage. I'll just wait a little. And I think the librarian has been so kind as to put some really lovely books out on display, all dealing with particle physics. So I think after the talk, I would really urge you to look through some of the books and decide that you want to borrow some of them. They're all absolutely suitable for this audience, I would say, and it's a really lovely collection. Okay, so 130 years ago, because there's a book here which says Student's Guide to Maxwell's Equations, right? So let us begin there. You know, that Mr. Maxwell, somewhere in the late 1900s, what is it called? Yeah, 1895, 1896, wrote his famous equations, right? And all of you have seen them. All of you know Maxwell's equations. It's not mentioned in that slides, but basically we know that equations tells you what? Light is a wave, right? Electromagnetic waves exist. They travel at the speed of light. Light travels at the speed of light. But that's a very famous constant that was discovered there. It's related to square root of mu naught epsilon naught. For those who don't understand, forget about it. But there are waves, and these waves have two definitions in both space and time, right? Because a wave is a periodic object which goes up and down. The distance between two peaks or two valleys in space is called the wavelength. And when it propagates in time, the distance between two peaks or two valleys is called the time period, right? So these are two different objects. One is in space, assume it's moving in the z direction. One is in time, moving in a different dimension altogether. And so the wavelength and the time period, the inverse of the time period is called the frequency, are actually two independent quantities which describe this wave, right? Because one is the spatial description and the other is the time component, right? But these two are actually related. They're related because of this velocity of light, c, frequency times wavelength, right? C is equal to f nu lambda, n lambda, whatever is the favorite notation that you have, right? So they are not independent of each other. So that means the progression in time is actually related to the progression in space. And this will repeat again and again in particle physics. Oh, you're looking for chairs? Can someone, are there some more chairs which they can use? Some people at the back need some chairs, sir. Okay, yeah, they will organize something. Just give them 2 minutes, okay? So this constraint between space and time will occur again and again, okay? And already you know one constraint which occurs when we talk about Einstein's special theory of relativity. What is that? Instead of looking at the distance between, say, me and this, oh, this is a camera, I guess, in 3 dimensions, right? I can look at it in 4 dimensions. Of course, right now, both of us are static, but as I'm moving, you can think of a line in space-time. So not just the physical distance x, y, z between us, but in a dimension which includes x, y, z, and also the time component. So special relativity, again, just like you saw with c is equal to nu lambda, relates the time and space components in such a way that, I think almost back. Okay. We are not, is this better? You can hear better at the back? Okay, fine. Okay. Do you have a column height? It's okay. It's okay. No problem. I'll manage. Okay, it's difficult to wave your hands when you're holding the mic, but I'll manage. So I was saying that therefore you have a special space-time dimension now that Einstein introduced, and you'll see that Einstein thought of it in a very geometric sort of sense. Oh, we still don't have anything.
Yeah, one more.
No, I will wait. Not a problem. I think they're all understanding. I'm just giving some very introductory speech. So it's okay. All this they all know. I can see the bright and shining faces who are understanding everything. So what they say is that if I look at say if I make the corner of that room my x equal to y equal to z equal to 0, then the distance between these 2 points is your usual, or distance squared. Let me forget the square root is x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. And when I time dimension, it becomes minus t1 minus t2 squared. So there is a very famous minus sign. And the way to look at it is that you're not in flat space anymore, because this is flat space, right? I mean, if I were to fly, I could move in x, y, and I could fly up in z, right? So therefore, x squared and y squared and z squared come with the same sign. But you can think of Maxwell's equations, or you can think of special relativity as coming with a net relative sign between space and time dimensions. This has a special name. It's called Minkowski space-time, after the gentleman mathematician who invented it. In maths, everything is invented, nothing is discovered. In physics, things are discovered because the universe satisfies certain physical laws which we have to discover. I cannot make my own law of physics, because if nature doesn't reflect it, then, but the mathematicians have a good time, because, they can always invent something, and maybe, physicists can use it, but if we can't, it's still a good thing, right? It's still a theorem, it's out there. So that's an invention, right? So they invented a lot of things. And one of them is Mr. Minkowski, who invented Minkowski space-time. It's still a flat space, right? Because there's no curvature, nothing. It's just equal proportions of space and time. If I had one x and one t, I'll just have x squared minus t squared. What this leads to is a geometric definition of mass. Now, this is something that I will come to at the end of the thing, but this is something that I can, okay, so here we've gone over all this. This is for those who are still in. Can you turn on this? I'm practically at the beginning, don't worry. No, yeah. Yeah. Yes. Pointer won't work on this, actually. It's okay. Oh, no, it's still not working. Oh, it's just slow, I think. No, I'm not able to get this to work. Right. Yeah, right. So unfortunately, the pointer will not work. So I can just point to you that there's no error in the speed of light. I'm not going to give you the answer. You can think about it. Okay. This is the speed of light today. Okay. It's about 3 to 10 power 8 meters per second, 30 centimeters per nanosecond. That's much, 1 foot, right? 30 centimeters. It travels a foot in a nanosecond. So it's really fast. And I already went over all this. So I was going over mass, but since this picture is, I could not show you this picture. It is a very interesting thing. When you want to do particle physics and you want to survey the universe, you have to survey it, therefore, in things like electromagnetic waves or other waves, or, you have to observe, right? You have to have some observation point. And so you have different kinds of, okay, again, this will not work. You have different kinds of radiation. We already looked at electromagnetic radiation, which is what Maxwell said. There's particle radiation, which of course makes everyone terribly afraid. So whenever you say radiation, people think of nuclear radiation, right? And you know how, Kudankulam or Kalpakum is contaminating the air, but it's also electromagnetic radiation is also radiation, right? They're just non-ionizing radiation. Even sound is a radiation. You can listen to me. Gravitation is a radiation. So all these are given the name of radiation. Whereas, this pointer and this mic and the chairs are all considered matter. So the original people thought of matter and radiation. So universe is either made up of matter, and what fills the matter in between space of matter is called radiation, right? But I want to focus on this particularly, that this is actually our Earth's atmosphere. Very interesting thing. So it's completely besides the point, but I just want to highlight to you. And since it's not visible, I think to people at the back, I blew it up in the next slide, if it is willing to move there. Okay. So I have just taken the leftmost portion, which is the larger wavelengths. Okay, you can see, I hope you can see, this is called radio waves, and these are microwaves. And this is the opacity of the atmosphere. This is 100% opaque, and this is 100% transparent, and then it becomes opaque again. So you can see that radio waves, so the atmosphere is transparent to radio waves, which is why you can hear the radio, okay? If the atmosphere would not allow radio waves to be transmitted, there will be nothing called the radio, it would not have been invented. And if you look at smaller and smaller wavelengths, this is the ultraviolet X-rays, gamma rays, you can see it's completely opaque to those radiations. And there's a very, very narrow window here around 10 power 15 hertz, and actually there is a visible region. Not only the sun, we can see the sky around us simply because our eyes have evolved to look at this radiation in the visible region. I think this is something fascinating for me. Whether evolution evolved so that it could see, I mean, which way it goes, A to B or B to A, I don't know. But I find this the most fascinating thing, that if our atmosphere had not allowed visible wavelength or wavelengths in which the sun is mostly emitting, then there would have been nothing to see upstairs. We would have probably not even seen anything on the earth, right? Because sunlight is the only thing which allows us to see on the earth. So that is kind of a completely besides the point story, but I find fascinating. So you can see that all observatories where we want to observe the universe, if they are earth-based, must observe, for example, in the radio or in the visible or in any region where the light from those distant galaxies can actually pass through the atmosphere and reach us. If you want to observe in wavelengths which don't reach us, then you better go outside the atmosphere and put it on a space-based satellite, right? Okay. So now we come back to light. We have heard light is now part of radiation, and we thought of matter and radiation as being different. And now we come to the beginning of quantum theory. I didn't show you my outline of the talk, but now we're coming to how we understand quantum theory, that not only is light a wave, it also behaves like a particle. And in its particle avatar, it's called a photon, and its discovery led to the birth of quantum theory. And this quantum of light says that anytime I'm given either a wavelength or a frequency, because they are related, c is equal to nu lambda, the frequency or the wavelength immediately determines for me the energy of that wave packet which represents that light wave. And this proportionality constant is called Planck's constant, because Mr. Planck was the one who actually gave the theory for this. It's a very long and nice this thing, about just at the turn of the century, so about 125 years ago, people actually discovered that light is both a wave and a particle. So you think of electron as a particle, now you can think of photon as a particle also. But however, even though now you know that a photon can behave as both a wave as well as a particle, so it has a dual nature, it turns out that even matter has dual nature. So I'm made up of atoms, and atoms have electrons, protons, neutrons, whatever. And these particles also have a wave-like nature. So the particles also have a wave-like nature, but this wave-like nature is very special. What is special about it? That the wavelength, again, that same Planck's constant h appears here. The wavelength is related to the inverse of the momentum, which means that if I'm standing at rest, if I think of myself as one single particle, just stretch your imagination, then the wavelength will be infinite. So there is no more wave associated with me. But the moment the particle is in motion, I can associate a wave with a particle as well. So photon, which we thought of as radiation, has both wave and particle nature, dual nature. And electron, which we thought of as particle, also has dual nature, both wave and particle nature. So then what is matter? What is radiation? Because everything is like a particle, everything is like radiation. So how do we now look in the modern way? How do we look at what we call high energy physics or particle physics today. So that's really what I'm going to talk about, right? When I say what is the universe made up of, what are the fundamental bits of which it is made up of? And certainly I can't say particles or waves because that doesn't seem to be the right way to look at things anymore. So we come back to this relationship, as I said, between space and time that we talked about, has been recast in quantum mechanics by Mr. Heisenberg, called the Heisenberg's uncertainty principle, which many of you have learned about. But this is the cornerstone of all of quantum mechanics. It is the cornerstone of all of particle physics. And what does it say? It says that the uncertainty in momentum times the uncertainty in space has always to be larger than some small quantity times h, where h is the same Planck's constant. It also says that the uncertainty in energy times the uncertainty in time is also the same, greater than h. Now, if you look at time and space now, Einstein has related them. So either we talk about momentum or we talk about energy, they're the same thing. Sorry, this won't work. It says that therefore some energy associated with an object of some size are inversely related to each other. This is the ultimate boiling down of Heisenberg's both uncertainty relations in the relativistic limit come to the same quantity. Okay, so the energy is proportional to 1 by distance. Here I will give 2 examples. We know that the hydrogen atom has what inside it? 1 proton and 1 electron. So now I say that let's take this part of the room where we are all standing, and let me call it 10 meters, right? Suppose I say that the hydrogen atom's nucleus, that means the proton, is the size of this room, so it's about 10 meters in size. Where will its associated electron be? That is the calculation I'm making over here. The calculation I'm saying is that we know that any atomic distance is of the order of angstrom, which is of the order of 10 power minus 10 meters, but anything associated with nuclear sizes is 10 power 5 times smaller. So nuclear sizes are in units of Fermi, which is 10 power minus 15 meters, right? So it is 10 power 5 times smaller. But this equation now tells you that if something is 10 power 5 times smaller, the energy will be 10 power 5 times larger. So let us calculate 2 quantities, okay? We have the factor between atoms and the associated nuclei as 10 power 5. So if the nucleus is, or the hydrogen atom's proton, which is the actual nucleus itself, is of the order of 10 meters, where will its associated electron be? Will it be inside Chennai or outside Chennai? How many people say outside? How many people say inside? How many people have no opinion? No, please have opinions, okay? So it has to be, if the size of the proton is 10 meters, where will its electron be? It will be 10 power 5 times 10 meters away, right? That is 1,000 kilometers. It will be in Bombay, right? So that means if the proton is the size of this room, its associated electron is in Bombay. It's actually talking to this proton. It is associated with it by electromagnetic attraction. It is bound to it because it's an atom, it's not an ion, but it is talking to it all the way from Bombay. So there are 2 things. One is that electromagnetic attractions are relatively weak, obviously, because the electron is so far away. The other thing is that the atom is mostly hollow. This is something they never teach you in school, but this is what actually drives all of particle physics. Because between the energy or the distance scale of atoms and the distance or energy scale of nuclei, there is nothing in between. There is an electron, here is the nucleus. Is it clear? So the moment I stop talking about atoms and what electrons are doing, electronic transitions, right, which make up your microphone and all electronics equipment and my phones, stuff like that. After that, I have to give 10 power 5 times more energy to do anything with the nucleus, right? Only then I have nuclear transmutations. And that is why per gram of matter and per gram of nucleus, Kalpakam is generating so much electricity using so little of uranium, simply because per unit mass, you get 10 power 5 times more energy because the energy associated with it is 10 power 5 times more. But what is this energy called? This energy for the hydrogen atom, even though the electron is in Bombay, I can essentially take this electron away to the edges of our universe, right? That is called ionization. And please remember, universe is finite, right? I hope all of you know our universe is finite in size, it's finite in age, but we always talk about taking something away to infinity, and that is what we call ionization, right? So you have to stretch your imagination to send an electron away to infinity in a finite size universe. But once you have accomplished that, you have an ionized atom, right? You have a positive ion, right? And how much is the ionization potential of hydrogen atom? Everyone learns this in school, right? Does anyone remember how much it is in electron volts? Okay, everyone says 13.6 with a decimal place. Okay, so but what does it mean? So let me call it 10 electron volts, right? The moment I say 10 electron volts, I know that nuclear transmutations will be 10 power 5 times that, which is millions of electron volts. Okay, that is why, as I said, I get so much more energy out of Kalpakam or Coulomb Coulomb, and why we should say no to nuclear bombs, right? Because they are so they are 10 power 5 times more devastating than your Diwali fireworks or your dynamite or whatever nonsense, right? So this scale, therefore, which Heisenberg sets for us, tells you that I can either view something in terms of its size or in terms of the energy equivalent. So I say that if I want to probe something smaller, I must probe it with something higher in energy. And that is why particle physics is also called high energy physics. Because I want to probe deeper and deeper inside the atom, I must have higher and higher energy if I want to probe smaller and smaller distances, because Mr. Heisenberg has said so. Okay, so okay, so this I think I have already done, so I don't want to go over it. Okay, except that we come across, I said 13.6 electron volts was ionization energy, right? But I don't need to completely ionize. I can send it from one orbital to the next orbital. I can send it to excited state, various things, right? So whatever it may be, some energy is required in order to bind the electron to in order to remove the electron either from the ground state to a higher excited state or to ionize it completely. Conversely, when an electron binds with a proton to form a hydrogen atom, 13.6 electron volts of energy will be released. Right? They are two sides of the same coin. So the same thing was found almost exactly 100 years ago. So I want you to also, the reason I'm giving years is that, the science is very young. 100 years is not much at all. But the amount that we have studied and how we've actually harnessed this technology, and our world is completely a quantum world today, right? It has moved so fast, and I want you to appreciate that, actually. I hope you can appreciate that. What Aston found was that 4 protons are heavier than 1 helium nucleus. And helium contains 2 protons and 2 neutrons. And those of you who know that the neutron is slightly heavier than the proton. So in fact, this seems very non-trivial, right? This should have been heavier than this, because 2 neutrons are heavier than 2 protons. So this should have been the other way around. But what happens? 4 protons are simply sitting there as 4 protons, whereas the helium nucleus, again, is bound together into a nucleus. And that same thing happens like I had with a hydrogen atom and its hydrogen nucleus and its electron. There's a binding involved, and the binding energy gets released, and therefore this becomes lighter. It has lost a certain amount of mass. Is this clear? And that energy that it has lost is what makes it, first of all, stable. It's a very stable nucleus. And also, it also tells you that there is something called binding energy associated with formation of nuclei. And this diagram, I'm not sure you can see it from the back. This is the mass number, which goes up till uranium-235. 1 is not there. It starts with 2 because 1 is not a bound. It's just a single proton. So it starts with deuterium. And this is the binding energy per nucleon. So binding energy divided by A. So it tells you that binding energy keeps increasing up to you go to iron or silicon. And then again, it starts decreasing until you come to the larger elements. So the way to understand this is the following. Suppose in some way I'm able to bind, say, 1 proton and 1 neutron into deuterium. It has this binding energy, and we know it's 2.2 million electron volts for those who have done nuclear physics, right? Some 2 million electron volts. And then if you can bind further to form carbon, nitrogen, oxygen, the binding energy is more and more and more. So what happens? This is called nuclear fusion. Its advantages to take light nuclei, fuse them together, get heavier nuclei, because energy is released in the process and you get stable nuclei. And you do this all the way up to iron. Conversely, if you start uranium and you break a uranium into, say, 100, so from 230 you go to 120, then of course, again, the binding energy increases, and this is called nuclear fission. So nuclear fusion and fission can be spontaneous because energy is released in the process. In chemistry, you'll call this exothermic reaction, right? So what happens to iron or silicon sitting over here? It neither likes to fuse nor it likes to fission. And this forms a very, very important role for the formation of our physical universe, and I will come back to this at the end of our talk. So please keep this in mind. The nuclear binding energy tells you that light elements like to fuse. heavy elements like to fission, and iron and silicon don't like to do anything at all. In fact, whether this turns around at iron, silicon, nickel was a very big open problem in nuclear physics and was solved only recently, actually. So what are these interactions now? Now I'm going to go over to, I have given this example of electrodynamics. I've now introduced to you nuclear physics. I've told you how nuclei bind. So these binding forces are due to some interactions. And now we understand in our universe, there are 4 fundamental interactions. What are fundamental interactions? Somewhere we have broken down our universe into the smallest set of particles, the fundamental objects which make up our universe, which I will write down in the next slide. And these fundamental particles experience only 4 forces. So fundamental particles experience 4 forces, so they're called fundamental forces. Otherwise, there's nothing fundamental about them. So I'm standing here, and there's friction which holds me to the ground, and friction is just the electrostatic force. So it's a derived force made up of some combination of other forces. So the 4 forces are only gravity. Of course, we all know gravity is one of the oldest known forces. Electromagnetic, we talked a lot about Maxwell's equations. The strong forces, I told you, holds the nuclei together. That's what causes the binding. And the last one that we haven't yet talked about is actually the most ubiquitous after electromagnetic, not even, maybe even more than the electromagnetic interactions. It's called a weak interaction simply because it's much weaker than electromagnetic interactions. And they're called strong interactions because they're stronger than electromagnetic interactions. And actually, on this scale, gravity is extremely weak. So when we talk about particle physics, we leave out gravity. Normally, we don't talk about gravity in high energy physics. If you want to talk about string theory, that's where gravity appears in your theory. But otherwise, in the standard model, there is no gravity. You only have these 3 interactions. So the example I can give is proton is positively charged. So the way now we look at how a proton binds with an electron, which is the paradigm of particle physics, which is what I'm going to talk to you about in the next few slides, is that a proton and an electron, the way they interact to form a stable hydrogen atom is through electromagnetic interactions, right? Positive charge and negative charge attract. And what you say is that there is something called a photon. This photon symbol is gamma. This gamma is now a particle. It's called a mediator particle. And all particles interact by exchanging different mediators. So if the proton wants to experience electromagnetic interaction with any other particle, it exchanges a photon with that particle. If it wants to experience strong interaction with some, say, another neutron or proton inside the nucleus, it exchanges a gluon, which is the mediator of strong interactions. And if it wants to experience weak interactions, or when it experiences weak interactions, it exchanges 3 kinds of particles: W plus, W for weak, W minus, and Z. I forgot to put Z0. So photon, gluon, and Z are all charge neutral particles. W is Z plus minus. So this is the basic paradigm of particle physics. What did we think of in the old days? What did Newton say? 2 objects collide and then they scatter, and the energy momentum is conserved. Here, 2 particles never actually collide. When they approach each other, they simply exchange particles. The exchanged particle will determine the nature of the interaction. If it exchanges gluon, it's a strong interaction, and so on. And then they will scatter off again with each other. So this is now the paradigm. And in fact, what happens is that the template was given by electromagnetism, and this template was applied again and again and again, and always found to hold. So you just increase that, made it a little more complicated, you could allow for weak interactions. You made it a little more complicated, you could allow for strong interactions. So you find this is the paradigm of particle physics. So what is this template that you use? It has to be something that is consistent with special theory of relativity, because that's what we started out with. That because we always think of space and time as being related, that happens only in special relativity. And then, depending on whether you have 1 photon, 8 gluons, or 3 weak mediators, you have to have certain symmetries of the theory. So technically, if some senior people are there, you have certain symmetries of the Lagrangian. And this symmetry is what tells you what is going to be the nature of this interaction. Okay, so the way you count 8 gluons, 3 weak bosons, or 1 photon is to look at what the symmetry generators will give you, and that tells you how many mediator particles there are. But as far as we are concerned, if 2 particles exchange W, for example, every particle in the universe will experience weak interactions. Then if 2 electrons interchange a W or a Z boson, then you will see that they will interact only weakly with each other. Okay, is this all right? So this is the modern understanding of particle physics. And okay, this is an aside. I'm not sure whether I want to, okay, maybe I will talk about it. Already 11:30. Okay, fine. So we know E is equal to mc squared, which is the most famous equation ever written. If I say, tau is equal to lambda by, say, j powers 2, then you will not recognize the equation, but I could have redefined everything, but everything is in the notation, right? When you say E equal to mc squared, the actual equation is actually this. The square of the energy is P is the momentum, M is the mass, and C is our velocity of light or speed of light, actually, technically correct. So, and if you find the square root of this and you take P equal to 0, you will get E equal to mc squared. Now, when Einstein wrote this equation, he essentially said that if I have a mass of a particle, then mc squared is the energy equivalent of that particle. So this is what the energy mass relationship means, which means that if you remember, no one asked me this question, when Aston found that helium is lighter than 4 hydrogen, there's a certain mass difference between 2 proton, 2 neutron bond system and 4 protons. And this mass is converted into energy by putting a c squared over there. But it's not simply putting a c squared over there. This energy is actually genuinely there. Because if I take, and this is something that Einstein did not know, Einstein wrote this in 1905, and almost 20 years later, Paul Dirac actually wrote an equation for particles which have something called an internal quantum number called spin. Now, it doesn't matter what spin is. In school, you learn it as how electrons are filled into orbitals, right? So that is sufficient for us. However, he introduced 2 notions in his equation. So apart from spin, he introduced the notion of antiparticle. Until then, people did not know that antiparticles exist, that antimatter exists. And we know that a positron, which is the antiparticle of an electron, has exactly the same mass as a particle, as the electron, okay? But it has other quantum numbers are all opposite to that of an electron. So if an electron and a positron meet, they will annihilate and they will actually produce photons. And what photons will they produce? They will produce photons with energy equivalent twice mc squared. If m is the mass of the electron, m is the mass of the positron, when electron-positron annihilate, they will produce twice mc squared photons, actually genuinely get energy out of it. So this mass is actually completely convertible into energy, not just in the equation, but in real life. And this is where the quantum mechanics gets elevated into something called a quantum field theory. Because you see that in quantum mechanics, you say that if I have an electron, quantum mechanics tells you what is the probability of finding the electron here or there at some time, later time t. So, and the total probability is always 1. But here, when an electron meets a positron, after that time when it is annihilated, the probability of finding that electron is 0 because it has become photons. So something else is conserved, right? So I can have particle number changing and some other quantum numbers will be conserved, and that is when, I won't go into the details, the quantum mechanics, relativistic quantum mechanics theory that you had now gets elevated into a quantum field theory. I really apologize to those who are standing. I'm sorry, okay? I cannot do anything about it except that I'm also standing, so I'm in solidarity with you, okay? Okay, so this is about antiparticles, right? So this is the meaning of antiparticles, except that if you look at p squared as px squared plus py squared plus pz squared and bring it on the left-hand side, I have an equation. Just let's forget all the c's. Let me put c equal to 1 for now. So this equation can be read as e squared minus px squared minus py squared minus pz squared equal to m squared. And therefore, you can see that this looks exactly like your time, comma, minus x, minus y, minus z, that space-time that I talked about, Minkowski space-time. And in fact, this is a vector in the Minkowski space-time, and you can see that the invariant quantity associated, like how I had an invariant space-time distance between this camera and me was constant in Minkowski space-time. You can see that the mass, therefore, was interpreted by Einstein as a geometric quantity. It is an invariant quantity appearing as the constant between E squared minus P squared in that 4-dimensional Minkowski spacetime. So you can see that mass keeps getting again and again redefined, because in school, what did you say? Inertial mass is the amount of matter contained inside it, which means exactly nothing, right? What did you understand from it? I never understood anything. I never asked my teacher. Probably at the time, teacher also did not know, right? That's how we just go. Either you get your marks in the exam and you're happy, right? But mass is something that is still an open question today. I don't think that the question of what is mass has been really solved. And when when Einstein talked about general theory of relativity, he talked about something called gravitational mass. And then people proved that this inertial mass of the particle, which Newton talked about, and gravitational mass are the same thing. But it's like saying x equal to y, but we don't know what x or y is. But they are the same, right? So this thread will go through all the way when we come to the next few slides as well. But this is the thing about mass. So the mass actually is an energy equivalent. It can be extracted by annihilating that particle against its partner antiparticle. So you can actually see that energy physically. And so I now put together all this information that we have got and write down a periodic table of elements. So just like you had a periodic table of atomic periodic table, here is my periodic table of elements. This electron is very familiar. I hope you cannot see the bottom part. I think people are having difficulty with the bottom part. I think, I'm sorry. Anyway, we have the electron which sits outside the nucleus, and there are heavier copies of the electron called mu and tau. So they are put in 3 columns like this, 2-dimensional vectors like this, and each has a partner particle called a neutrino, which is charged neutral. So there's a nu e0, nu mu 0, nu tau 0. And these are all called leptons. Now it turns out that what you thought of as a proton is not indivisible. Again, the old story, right? Atom is that, indivisible unit of which all matter is made. But then in higher classes, they say atom contains a nucleus. And nobody said, oh, but you told me it was indivisible, right? The same story repeats again. So not only is atom not indivisible, but even protons are not indivisible. They are made up of more elementary objects, which are called quarks. And it turns out that protons and neutrons are made out of this first generation of up or down quarks. But there are heavier copies. They have very strange names: up, down, charm, strange, top, and bottom. Okay, and there is a very important reason that if there are 3 generations of quarks, or what we call baryons, because protons are there are also 3 generations of leptons. That is required for the theory to be consistent. And in fact, exactly these have been found in nature today. The top was found last. It's extremely heavy. It's about 200 times heavier than the proton. So, but it's still a building block of matter. Okay, it's an elementary particle. Fine. So this is now our periodic table. And along with the periodic table that's why I put this again, come the gauge mediators, gamma, G, W plus, W minus, Z, and then one more particle, which I will talk about in the end. So I think since we are a little bit short of time, I will not go over this part. This is something about the mediators of various interactions. I can share my slide with people, and those who want to see that intermediate part, intermediate part will. Sorry, wait. Sorry. I don't know what happened. Here we are. So, okay. Yeah. Yeah, so you should remember that an LED screen will not either react to this or to a pointer. So that is you can find out why actually. It's a property of the LED screen. Okay. Huh? It's perfectly all right. I just need to do that. So anyway, so the last particle that was not mentioned till now is again another definition of mass. And this is, people call it the God particle. The God particle is a complete misnomer. I don't want to go into the history or the etymology, but the Higgs particle is actually just, okay, I forgot to say one thing. So when we talk about a quantum field theory, we no longer talk about electron as particle, but we talk about electron as field. We no longer talk about U quark as particle, but we talk as U quark as field. The reason we do that is because, as I said, it's neither a particle nor a wave, right? So loosely, you can still call electron a particle, but correct technical word is to call it a field. So these are all fields, okay? And just like you have electron fields and quark fields, you have the Higgs field also, whose particle avatar is called the Higgs particle, which was called the God particle, which was discovered about 10 or 12 years ago. But this is a very special particle because it says that interaction of any fundamental particle with the Higgs boson, it's a boson, it's not a fermion, will give mass to that particle. So when a U quark interacts with the Higgs field, it gives the mass to the U quark. When an electron interacts with the Higgs boson, it gives mass to the electron, and so on. And it's like the very nice analogy that I found. this won't work, is like a ship on an ocean. So the ship is the particle and the whole ocean is the field, and the kind of the drag of each ship will be different, and the drag is really the mass, and the waves of the ocean are the Higgs particle. So the ocean itself is the Higgs field. The waves form the particle of the Higgs, and the interaction of this with the Higgs field will give you the mass of the particle. And so now you have a new interpretation of mass. You know, now no longer have inertial mass, gravitational mass, geometric mass, but now you have mass as an interaction of particles with Higgs field gives mass to that particle. I'm sure the last word on this is not written, because the way in which this interaction arises is extremely complicated, because for those who know what a Lagrangian is, if I directly put a mass term in the Lagrangian, my theories will be highly inconsistent. So instead of touching my nose like this, I have to touch my nose like this, and then everything works out fine. And therefore, it becomes extremely complicated. But in order to save the symmetries which give these interactions, I have to do this process. So no one understands why it happens or how it happens, but it seems to happen correctly. It gives all the right interactions. It gives all the right results. So we know that there is a Higgs field. We have actually found the mass of the particle. We actually believe that the Higgs has self-interactions. I skipped those parts. Gluons, Ws, Zs, and Higgs all have self-interactions. The self-interactions of all other particles have actually been checked out and discovered and verified in the lab. Self-interactions of the Higgs is still an open problem. We believe that it's there. We don't know that it's there. So we come finally to the question of, I said, what is the universe made up of? All these particles. How do we know this? I'm going to give a very short and very kind of superficial treatment of it. But I think it's very important because physics is actually an experimental science. So each of the statements in the preceding slides has been experimentally verified. The example I have skipped over, I apologize, it doesn't matter. This lecture is too short. It's a very convenient excuse to describe all the beautiful experiments that led us to this. But I will give you a few examples so that you understand how we have probed and understood our physical universe. So one thing I want to always highlight, I think serendipity plays a very great role. It's important not only to be at the right place at the right time, but you have to make the right deductions. That's what makes you a scientist. You can be in the right place at the right time with your eyes closed, and then you won't get any Nobel Prize, right? Of course, I didn't get a Nobel Prize, but maybe I wasn't with either eyes closed or not in the right place, right? So all these are all, you can decide your combinations. But these are some nice examples. I think penicillin is the best known. That, Alexander Fleming was supposed to be extremely careless and chaotic and dirty, and he left his petri dish near an open window, went away for vacation. But when he came back, he actually interpreted nicely that whatever was there in his petri dish was penicillin, and then he discovered penicillin. So you can be dirty, but you have to actually observe well. Similarly, discovery of X-rays, invention of the WWW, all of us, I think, will be lost without World Wide Web. Some very practical discovery, this I love this example, George de Mestral going in the Swiss Alps with his dog, which had a lot of fluffy hair, and these thorny bushes used to stick to it. And he used to take hours to remove those thorns. And then he figured out why it is that, it binds so well with the fur of the dog. And then he invented Velcro, which I think is an amazing discovery, for people who can't tie shoelaces, like one of my daughters can't do it. And then this Velcro was an amazing discovery. Okay. So, of course, there are also certain phenomena which are observed before even they are predicted. Okay. So both things can happen. You observe and then you try to find a theory behind it, or you have a theory and then you look for the prediction, whether it is validated or not, because as I said, physics again requires you to actually make contact with the physical universe. You can say that my theory will work in some other universe, but then please go to that other universe to test it. I think the laws of physics are very, very clear that we are talking about the laws of physics in this universe, right? So that is something we always have to make track with. So here is one short example on how stars die. So I already talked about fusion, right? And I think this is there in the 12th standard textbook, that the sun burns or shines through fusion of hydrogen into helium. So I think all of you who have done 12th standard would have remembered it. Therefore, 4 protons fuse together to form a helium nucleus. And in the process, 2 protons have become 2 neutrons. And we have already learned about binding energy. So that much energy is released in the process. And that turns out to be about 26 billion electron volts, of which a large part is actually coming out in the form of neutrinos. Very small part comes out as sunlight. But you can always look at the amount of sunlight, and then from there you can backtrack and ask, therefore, how many neutrinos are coming from the sun, and you'll find that it's something like through my thumb, which is 1 square centimeter, about 40 billion neutrinos are coming through per second. Okay, and that's an incredible number, and has actually been observed. A lot of physics has been done. Some 4 Nobel Prizes have been given in the neutrino sector. But that's all. As I said, you know all this stuff. But our sun is just another star, right? For billions of years, it has been and will be in hydrodynamic equilibrium. It is now 4.5 billion years old, as you can see over here. And what is the equilibrium between? When something is shining, because in the core of the sun, hydrogen is burning into helium, what happens with the hot gas? There's outward pressure, right? It wants to expand. But what is gravity doing? Gravity is always pushing. This is something, again, in school, they never tell you, two positive charges repel. Opposite charges attract. But in gravity, there is no sign at all. It's always attracting. Two masses, even if you have, it's not nothing to do with matter, antimatter, two pieces of matter will always attract. And gravity is an infinite range force. You remember that Newton said gravity is the force due to gravity is proportional to 1 by r squared. So it vanishes only at infinity. And our universe is finite. So it's certainly going to be turned on all the time. So gravity, if you have even a small mass somewhere, it is going to be attractive. In fact, that's how stars are formed in the first place. Okay, we are all actually, I don't know how you're sitting in the chairs, you're all attracting each other. Slowly, we should all be collapsing together, but it will happen on very, very large time scales because our masses are so small, right? But on the other hand, atoms are exactly electrically neutral because the electromagnetic forces are much, much larger than gravitational forces. So if the electron and proton mass, proton charge is slightly different, then all of us would have a huge amount of net either positive or negative charge. And forget sitting next to each other, you will not even be able to sit on a chair, right? Because both will have the same excess, same sign charge, and everything will repel everything, right? Is it clear? So you cannot do this. And why will it be very large? Even if there is a very, very, very small net charge difference between proton and electron. Yeah, because there are so many Avogadro numbers of particles in our body, right? Because 1 gram molecular weight has 10 power 23 atoms or molecules. So if you just multiply it out by 10 power 23, you can see how large those forces will become. So that is very important. So here, on the other hand, gravity is inexorable. It's always positive. It's always squeezing the star. It's just stable because the outward force, because anything hot is radiating outwards, the outward pressure is balanced by the inward gravitational pressure. And the sun has been in equilibrium, will be in equilibrium. The sun is a midlife star, will be in equilibrium for another up to altogether about 10 billion years. So it's like a middle-aged star. It's a very ordinary star, at which point, because it's cooling off, it becomes a red giant. And then when it loses all the energy in its furnace, it will die as a white dwarf. And many white dwarfs have been seen in the skies in our universe. So this is our star. This is our sun, our star. However, there are many other things that other stars can do. And this is something that makes the universe much more interesting than just having boring stars like our sun. So this symbol, M with a circle and a dot, refers to our sun. Okay. So if any other star in the universe has a mass which is about less than about 8 to 10 times our sun's mass, again, it just has the same behavior. The heavier it is, the faster the life cycle goes. So instead of billions of years, its life cycle may be just hundreds of millions of years. But basically, it will do nothing other than just the same life cycle that our sun has. But anything which is in the 8 to 20 solar mass region, I will show you in detail, the star actually collapses and produces what is called a supernova. Show you that in the next slide. And the supernova explodes, and what is left behind is a neutron star. I think neutron stars have been in the news because of LIGO. I'm sure many of you have been reading about it. And if you have something which is started out as a mass much, much more than 20 solar masses, it will actually collapse into what is called a black hole. And black holes have also been seen recently, not as long ago as neutron stars, but in the last about 5 to 7 years, black holes have also been seen. There is, in fact, we believe that every galaxy is actually powered by a central black hole. And our Milky Way galaxy, which is what our solar system belongs to, has a black hole in Sagittarius. It's called Sagittarius A star. It's a huge, I think, some 4 billion times the mass of our sun. There's a central black hole which basically drives our galaxy. Okay, so what actually happens in stellar collapse? We saw the sun, right? Sun hydrogen burns into helium. That is the starting point. Now, if you have a more massive star, it can squeeze the matter more because gravity is much larger. And so what happens is that after the central region where hydrogen is burning into helium, helium can burn into carbon, carbon into neon, oxygen. Now you have to remember your atomic periodic table, right? You'll keep going and producing heavier and heavier elements all the way up to silicon. So you have this onion layer structure of the star. And this hydrogen to helium will take millions of years. It becomes hotter. I mean, this takes hundreds of million years. This may take 1 million years. This may take 10,000 years. And silicon burning will happen in one day. And what happens when silicon burns? It produces iron. And now you have to remember that binding energy curve that I showed. Maybe I should just show you this binding energy curve again. Not very successful. No problem. I'm just going back quite a bit. Yeah. So here is a binding energy curve. So you can see that fusion happens until silicon burns into iron. And then everything is inert because I can't have fusion anymore. But what happens to gravity? Gravity is still squeezing, right? Gravity is still squeezing. So what happens suddenly in the core of the star? It's like almost like a furnace has turned off, right? Because there's no more burning in the central core. This, you can see this black portion, right? They're completely switched off. Outside, of course, I mean, here hydrogen is burning into helium, helium is burning into carbon neon oxide. All of that is happening. But in the central core, nothing, everything is switched off. But gravity is still switched on. It cannot switch off ever. So gravity will squeeze. In fact, in just 1 millisecond, it will squeeze the core like this. And this core has a very well-known mass. It's a very famous mass. This is called Chandrasekhar limit. It is unstable beyond this mass. And it squeezes the mass until it can squeeze it no further. And then it's like when you squeeze a ball and let go, it just rebounds. And so the outer part in the red just completely gets thrown off into the supernova explosion. And what is left behind the core is a neutron star. Okay, this is the whole process which happens, as I said, I think within 10 seconds, the whole explosion is over. Within milliseconds, actually, the whole core collapses. And the question is, what is left behind? Is it a neutron star or a black hole? That actually depends on how much matter is there. As I said, if it's a very heavy object, what is it actually that drives this thing? It's very simple. It's actually a old Pauli exclusion principle. Right? This is called electron degeneracy pressure. I cannot put more than 2 electrons in one orbital because of Pauli exclusion principle. Now what happens? Gravity is squeezing these atoms. And so what is happening? Their electron orbitals are overlapping. And they're getting squeezed so much that I'm trying to push more and more electrons into the same energy level. And so the whole thing collapses. What happens is that the protons in the nucleus, because they squeeze so much, are actually eating up the electrons in the orbitals outside. And the proton plus electron becomes a neutron. This is the neutronization of the core. So it's like every proton, and because of charge neutrality, there will be equal number of protons and electrons. So the protons and electrons keep finding each other and converting into neutrons to overcome this Pauli exclusion principle. They can squeeze more and more and more. And if the mass was not too high, it will simply become a neutron star. If the mass is too much, of course, even protons and neutrons are fermions. They also live in orbitals which obey a Pauli exclusion. And therefore, if the mass is too much, it will overcome that degeneracy pressure also. And what will be left over with is a runaway singularity, which is called a black hole. So this is the first 1974 detection of a neutron star. This neutron star is also called a pulsar. Many of these neutron stars actually emit jets. They have very high magnetic fields. So they emit jets of particles. If this is the neutron star, then the jets will go out back to back. So if one jet is in this direction, one jet is in that direction. And if either of these jets is pointing towards the Earth, we can actually detect these jets of particles. And such neutron stars are called pulsars. And Hulse and Taylor actually studied this. B stands for binary. It's a pulsar binary. So one of the stars is a pulsar and emits a jet, which you can see. And the other part of the other part of the binary is a neutron star, which is not a pulsar. So it doesn't emit anything. And they actually inferred that it was a binary because its distance was actually wobbling in an elliptical form. And so it's actually rotating around a common center of mass. They have almost the same mass. And this jet that you actually see has a pulse period of only less than 60 milliseconds. It's very, very fast. These pulsars rotate extremely fast. And what they noticed was that as these pulses, because as I said, gravity is always squeezing, right? So you have a binary, and these binaries are actually emitting gravitational radiation. So now we come to the first part where we're talking about gravity. So all matter, including me, we are emitting gravitational waves when we are accelerating or moving like in orbits like this. But the gravitational waves are also a form of energy. So, and we know that energy is a form of mass, right? So as these binaries are losing mass, they will come closer and closer to each other. The orbits will shrink. They will come closer and closer together. That will get reflected in the period. And that period, that shift in the period has been actually plotted over 30 years. That is amazing. One of the most precise and amazing and long time measurements ever made. And you can see that the parabola, which is in blue, is the theoretical prediction if gravitational waves have been emitted from these pulsars, from the binary actually, both are not pulsars. And the red dots are actually the data, which first Hulse and Taylor, and then Taylor and one of his collaborators took up till 2005. And you can see that they actually sit bang on top of each other. So here is a neutron star, the first neutron star that was discovered. It was a pulsar. And here is its behavior according to what Einstein's theory of gravitation tells you. And they are bang on each other. And this was done using this telescope in Peru. And more recently, there is a very famous set of experiments called LIGO, two experiments in Hanford and Livingstone, and another similar experiment called Virgo. What they have seen is that you can have the universe is not a quiet place, even though the stars at at night when you look at the stars, which you cannot do in Chennai anymore, but you go to some place where there's not so much street lighting and you look at the stars and it looks very peaceful out there, but it's not. It's really like havoc out there. Things are exploding, things are merging. So these are experiments which look at merging of two neutron stars, mergers of one black hole, one neutron star, mergers of two black holes. Everything has actually been discovered in the last half a dozen years or so. And this is an example of merging of two neutron stars. You can see the signal, very, very faint over here. The signal is actually the audible frequency. It's a very complicated experiment. I don't have time to tell you about it, but it's like Michelson's interferometer, which you might have studied in college. It's similar to that, and it tells you that if I have two perpendicular uh, 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 lengths, where the photons go up and down, but they're not going up and down in vacuum, because now a vacuum is actually something which is being surrounded by a lot of matter. So if a gravitational wave comes, it will actually distort the space-time itself. And that will be reflected in the way we see the interference pattern in the experiment. It's a very, very beautiful and sensitive experiment. You can go and read about it. And this is therefore the proof that these neutron stars exist and that their mergers have been seen exactly according to what the theory tells you. On the right-hand side is again a very famous image. It's a radio image of a black hole itself, which is at the center of another galaxy which is close to us, called Messier 87. So a black hole actually is the object which you cannot see in the middle. The black portion is where the black hole is. The light that you see is actually electromagnetic and other radiation which is surrounding the black hole. Okay, so the black hole itself is not visible, but the characteristics and the features of this exactly matches the predictions of what you will imagine the black hole event horizon and its outside to look. So this is again an example that this is also something that is predicted and seen. So now I ask this question: what is it that we don't know yet, right? All this, okay, we have really exotic things I've talked about, right? Supernovae, neutron stars, black holes, everything has been detected. What is there which we still don't know about and which we are still trying to theorize about? And one of the main things is dark matter. So dark matter also, the evidence has come from the universe, from looking at galaxies far away from us. So you can see that now when we talk about particle physics, the decade before or 2 decades before or 3 decades before, people were talking about learning particle physics through collider experiments around the world. You collide two protons or electrons, positrons, or electrons with protons, and then look at the particle interactions which arise out of that. Today's particle physics actually is completely merged with astrophysics and cosmology. So the whole boundary is shifting. They're all become one subject called astroparticle physics. And so the dark matter is actually visible like this. So I'll first show you the data and then I'll tell you what the theory is. So you look at the galaxy. here is a galaxy. I forgot to tell you which galaxy it was. I'm really sorry. Anyway, so here is the distance away from the galaxy. And yeah, and here you can see that there are stars inside this galaxy, right? And actually there are stars, you can't see them, they're very faint, but there are stars all over, blue dots all the way out. But of course, they're very few in number and they are more densely packed here. Take any star, find out its distance from the center of the galaxy, and measure its velocity. What you can, of course, measure is the component in your direction. You can't measure transverse velocities, but you have a good idea of what that is from the rotation of this galaxy. And then you plot these things. Okay. So these are two different sets of observations, but they match, the yellow and the blue. And therefore, you can see that first, the velocities are in kilometers per second are increasing and then kind of flattening out. However, if you thought that this is the size of the galaxy, right? I can draw a circle over here. Then at the edge of the galaxy, the velocity should have peaked, and then it should have actually fallen to zero. But it's not falling to zero. In fact, if anything, it's rising or it's kind of staying flat. So what could be the reason for this, and why do we expect something to fall off is there in the next slide. So here you come back to Newton's law of gravitation, F is gmm by r squared. Right? This is something that you know. M is the larger mass, small m is the test mass, r is the distance between them. And now look at, suppose this is the Earth, and I'm standing on the Earth, so I know the value of g, small g. But if I keep going towards the center of the Earth, so if I'm standing here inside the Earth, then Newton told us that the gravity that we feel is only due to the mass contained inside this radius, right? So the outer parts will all cancel. So in fact, it happens also with electrodynamics, which has the same 1 by r squared rule, right? You would have done this conductor, solid conductor, hollow conductor, all those versions in Jackson. It's the same thing, right? So if I'm standing on the surface, then the gravity is due to all the particles inside. As I keep going inside, the gravity is due to only the mass that is contained inside that radius. And therefore, because it's a 1 by r squared law, you expect that to fall. And so when once I go away somewhere in this place, say I'm here far away, or if I'm here, or if I'm here, or if I'm here, this mass remains the same because it's just the mass of that object, but 1 by r squared keeps increasing. So I expect that it will keep falling as I go far away. And when I'm here inside somewhere, it will go from 0 to a maximum on the surface, and then it will fall. And that explains the graph on the previous page. So what does it mean that the velocity is staying constant? That means there is more mass, obviously, right? Otherwise, you could not explain this. So there is more mass, but it's invisible to us because I cannot see anything shining over there. So the mass is there, I cannot see it. That is the only thing that will explain those velocity curves. And this observation has now been verified in many, many different things, gravitational lensing in many different ways. And therefore, we know that there is some other matter which is actually there all around. It is also very dense where the visible part of the galaxy is, but it is also there out to about from 10,000 to about 50,000, about 5 times the amount of dark matter than ordinary matter. And that is what I have shown over here. So that means all this thing I said about, let me just drink some water. Yeah, thank you. Bad idea. Yeah, sorry. So all this that I told you, protons, neutrons, quarks, weak interactions, strong interactions, everything that we talked about is only explaining about 5% of our universe today. So all that stuff that we have done in the last 100, 150 years is only explaining very small fraction of the matter in our universe. And 5 times that is actually this dark matter, which we have observed, but we know nothing about. Does it have particle nature? Does it have particles with spin? It cannot have charge. If it has charge, it will immediately radiate. If it radiates, we will see it in the visible region. It is not radiating in the visible. Visible meaning not just visible to the human eye, but visible in the entire electromagnetic spectrum. So there is no electric charge, it has no magnetic charge, but what else can it have? So there are lots and lots of theories. I think there are more theories than there are data, but we have no idea because none of the theories has been validated either in astrophysical searches or in lab searches. And even more the only word I can think of is weird, finding is something called dark energy, which forms about more than 70% of the energy budget of our universe. And this is what is causing the universe to accelerate. Now we know that our universe is accelerating, but it turns out that distant objects are accelerating much more than nearer objects. So that means it's not just a central engine which is driving this acceleration. Because of this differential acceleration that we are seeing as we go to distant parts of the galaxy, and this is something which is extremely well established in the data. So we call it dark energy because it's an energy. We call it dark because we see no source of it. But without an energy, you cannot actually have acceleration, right? Because you need a force which needs an energy for acceleration. And so this is completely something that we simply have not understood. So this is a picture, from Wikipedia about how our universe looked at its formation, which is our universe is 13.71 billion years old, and how it looks today. And you can see that there was no central engine at that time. There was absolutely no blue color of dark energy. Dark matter was 2/3 of the universe, and atoms, including photons, neutrinos, were more than about 30% of the universe. And the whole thing has shrunk into something really weird and strange that we simply do not know. And I think all you young people who are interested should actually work on these ideas and see what we can understand about our universe today. Now, before I stop, so this is, as I said, we don't know all this. I'm not going to talk about this. I don't have time. The story of our universe is fascinating because I think it is the story of the only universe we have ever known. So should we be curious about it and want to find out how it works and what it contains, right? So before I end, I want to make a few remarks, and the remarks I can actually just stand aside. Why are we interested in fundamental science? All this is fundamental science, right? We're talking about how the universe functions. It's a very ambitious topic. Maybe it's also, in some sense, not doable. Maybe it's just too ambitious, but still we have found out much more than we ever thought that we could even 20 or 30 years ago, right? More and more discoveries have been made. But however, I think what I really feel is that these fundamental discoveries will have their own applications. Because, as I said, 100 years ago, the electron was discovered. Thomson discovered the electron. Why? Simply out of curiosity. He never wrote a project report saying that, we will do this, we will do that, it will have, 1, 2, 3 applications, right? He didn't write anything. He just did something, he found the electron, right? But today, I'm literally talking to you by means of electronics, which would not be possible unless we understood the fundamental properties of the electron, right? Our whole electronic world, computers, would not be possible without this discovery. Similarly, 100 years ago, positron was discovered. Today, we have PET scans, which save lives, right? We have X-rays, we have PET scans, we have MRI. What is a MRI? It's based on the physics of NMR, which is nuclear magnetic resonance. And even the discoverers of NMR said, if you put the word nuclear, people will be afraid. They will never have an NMR scan. So let us call it an MRI scan. And they dropped the letter N actually genuinely because of this, okay? But today, you're not afraid of MRIs. Maybe now you'll be afraid of it, but you should not be, okay? So all this is actually coming out of understanding of particle physics at different levels. Okay, and this is something I really want to tell you. It was not done because, I'm saying that all of what we do will have applications. But I think the human curiosity plus human ingenuity is such that many of these fundamental discoveries ultimately find applications, sometimes bad, as I said, but we should ensure as a society that we try to take the good applications and always make our life better. So these discoveries are actually not only developing a technology which is useful for more science research, but also for engineering and technology. And I think this is why it's important to do fundamental science. And this example I give because there is one person who asked, oh, what is the use of all these things anyway? In fact, what is the use of Einstein's theory of relativity? It is such an abstract theory. So for this person, I want to actually answer, and I have given this talk in many places. I always give this example. So how many of you don't have a mobile phone? There, the answer is 0, okay? So all of you have GPS, right? All of you have ordered Dunzo, Amazon, Insta, whatever, right? So how do you do this? There is a GPS on your phone. What is this GPS? There are more than 30 satellites orbiting our Earth today, and they're all giving exact time, very precise atomic clocks they carry. It's a very interesting science. Please look at it. And of course, when you turn on the location, without which, of course, no one can deliver to your house, what can you do? the satellites actually are circling the Earth twice per day. They are going at this speed. Now, Einstein's theory of special relativity says that there is time dilation. Time slows down when something is going at such very high speeds. And if you calculate that, it comes to about a difference of slowing down of the atomic clocks on the satellite by about 7 microseconds per day. But these satellites are actually very far away from the Earth. And I just told you that the gravity there falls as 1 by r squared, right? So the gravity there is less. In fact, it's exactly about 4 times smaller. And so Einstein's general theory of relativity says that when something is curving the space less, the clocks are actually ticking faster, and therefore it's faster by about 45 microseconds a day. In fact, the general relativity correction comes out to be much larger than the special relativity correction. So that means there is about a net difference of 38 microseconds per day. Okay, so or 10 kilometers per day, or it is something like few hundred meters in about half an hour. So if the delivery agent is about half an hour away from you, and you're getting some nice biryani or something, then sorry, but you're not even your neighbor, your next street guy is going to get it without your GPS connections, right? So without Einstein's both special and general theory of relativity, you cannot simply have no Swiggy, Dunzo, anything, nothing will work. Okay, so this is one example of this serendipity, right? Einstein didn't write his equations so that Dunzo guy can deliver to you, but it happens. Similarly, mathematics. See, mathematics is the language of science, but it also tells you other things. For example, all of you have seen this Aditya, right? Everyone has been talking about this Aditya solar probe. It's been in the news for the last few months. It was launched a few months ago, and it's sitting here. So you can see that this is the sun, this is the earth, this is the moon, absolutely not to scale. But you can, I don't want to spend time on it. There are certain Lagrange points called L1, L2, L3, L4, L5 Lagrange points. And this Aditya is sitting at the Lagrange L1 point, and this James Webb Space Telescope, which is giving amazing pictures of the universe, is sitting at the L2 Lagrange point. And these are stable Lagrange points where it takes very little energy for the satellite to last for a very long time. Okay, so this is important to know. So this is simply maths which tells you that's where you have to be. And Aditya is on this side, on the L1 side, because it wants to see the sun. And James Webb is on the L2 side because it wants to see the rest of the universe, not the sun, right? So this is the way you can even use mathematics actually to understand your universe better. So every fundamental science that you do, I think, it's very sad today that our funding in science is going down, apart from which the interest and enthusiasm of students in science is coming down. And therefore, I want to appeal to all of you. I'm not guaranteeing there are jobs in science. I think there are anyway no jobs anywhere today. So, but I think that if you're really interested in fundamental science, if you have high levels of curiosity, and you simply enjoy this kind of science, I strongly urge that you think about a career in science. And saying that we understand the world around us is a very, very hi-fi thing to say. But any small discovery that you make of your own, however small it may be, for those 10 minutes, you're the only person in the universe who knows that particular solution to that particular problem. It's such a great feeling. I urge all of you to think strongly about such a career, such young people. I hope you enjoyed the talk. I look forward to, even if one of you is enthused to do science, I think I would take that as a successful talk. I enjoyed talking to you all. Thank you very much.
See that very possible.
Yes.
During the particle interaction side, which you have explained.
Okay.
So one is it is going in the strong particle. Another one is we can produce in the weak particle. Then the slides is there. So it is what are all the reasons are in what situations it will, whether we can create it in the strong or whether it is a weak particle. Like
I understood your question.
that one
Yeah.
thing.
Okay.
Yeah.
Maybe you can stop there while I answer this, because I missed. This is exactly, you're asking me to talk about the slides. I skipped. You have to give me back the thing, otherwise they can't hear me. So this is the slide that I missed. If a particle can experience an interaction, it will never be switched off. Okay. So the thing is that which one will you see more dominantly depends on which is the stronger interaction. So this is an example of electron positrons annihilating into a photon. It will never annihilate into one photon. It will annihilate into two. Doesn't matter. This is two electrons repelling each other by exchanging a photon. This is what I said. This is how you understand it, right? So two photons can also experience weak interactions by, instead of a photon, exchanging a Z particle, right? Because that's a weak interaction. So I can interact by exchanging a W boson, or I can exchange a Z boson. All I have to do is to make sure that I manage my quantum numbers and I satisfy certain conservation laws. So energy momentum is conserved, right? Here what you can see, D quark is going to U quark. Now I didn't belabor the point, but the D and U quark have different charges. U has 2/3 of the positron charge, which is that is plus of the E charge, and D has minus 1/3 of the positron charge. So 1 minus 1/3 minus 2/3 is -1. So this W will have -1 charge. Right? So provided I can write these interactions down with the proper mediators, all of them will be allowed. Now you can see a neutrino becomes an electron, or an electron will become a neutrino. In fact, that will give you beta decay. Right? So we know beta decay is N goes to N, which is N has 2 Ds and 1 U, P has 2 Us and 1 D. So when 1 D goes to 1 U, that converts N to P. Okay. So that gives you plus electron. And if I bring the neutrino in the initial state to antineutrino in the final state, I get beta decay. So if I can write the diagram and I can conserve all my conservation laws, all my quantum numbers, which must be conserved, every one of those processes will be allowed. Okay. So that is how, that is the complexity actually of the theory. I just went over it very, very fast. But then you have to calculate if for example, as I said, both photon and Z boson can be interchanged. Then I have to add all the contributions, and my total observable will have contributions from each one of those processes. And that is actually seen. In fact, that is how the Z boson was discovered, by seeing that something is missing from just pure electromagnetic scattering, and therefore it had to be a neutral particle, and therefore the Z was discovered like that. So these are the kinds of ways in which you have to work the theory through. So these come from writing the Lagrangian and equations of motion. Yeah. Huh?
Big Bang theory.
Big Bang theory. Big Bang theory explanation is okay. Where do I start? Okay. I won't tell you what is the Big Bang theory. I will tell you the consequences of the Big Bang theory. Big Bang theory is exactly what it says. The universe began in a Big Bang. Okay. So when you say Big Bang in such a loose English fashion, it means that there is a singularity associated with the origin of the universe. It's exactly like a black hole. There is a singularity at that point because you have infinite mass in zero radius, right? That is the meaning of a mathematical singularity. That is where the universe also began. However, as the universe evolved to become finite size, and then atoms were formed, so ionization happens, then the universe cools, so then proton and electron actually cool down enough to form a hydrogen atom, and therefore the universe was mainly filled with hydrogen gas. And then, of course, there are certain fluctuations in this. So suppose in this place, for some reason, because statistically there can be fluctuations in the density, but when there is more density in one place, I told you gravity is always positive, always attractive. So wherever there is a little bit more density, there is more gravitational force, it will attract more of the matter around it. So it will become, that fluctuation will become even larger, it will grow and grow, and it will squeeze because of gravity, and the squeezing will cause the temperature to increase, and that forms a star. Right? So the universe starting in the Big Bang only gives you consequences for how the universe was not always static, in the sense that the universe that I see today is not just a variation, simple variation of how the universe was, say, 1,000 million years ago, or 5 billion years ago, or 20 billion years ago. It actually began in something where entropy is actually changing. So you start out with a point or singularity, and then you keep expanding the universe outwards. And now we know that this universe, because of the dark matter in it, it's an accelerating universe. It is simply going to keep on, see, because earlier there were these three possibilities. We did not know if the gravity is very large and the acceleration is not large enough. At some point, it's like something you throw and then it comes back to you, right? Because the gravity is pulling it back. And if your acceleration away from you is not large enough and gravity is more, ultimately it will come back to you. Then the universe will again close back into a singularity. There will be again another Big Bang, and again the universe will expand, and this chain can keep going. But now we know, because of all these dark matter, dark energy measurements, that the universe is simply going to expand forever. So it's never going to come back to a point. So there was one Big Bang, it's accelerating, and if you live maybe another 10 billion or 20 billion years, you can actually observe that The universe will be so cold, there will not be any energy to do anything. So universe will end in a cold death. So this is the difficulty of the Big Bang, is that it doesn't explain certain of the observations of the universe, like the distribution of matter contained in it, the distribution of galaxies contained in it. So you have to do something to fix that, and that is called inflation. Now that is just too technical. I don't even know how to start saying it, but think of it that way, that you had a Big Bang, and then that simple expansion was not enough. So in the early days, there was a very, very, very fast, almost exponential expansion of the universe. And then it slowed down and the normal expansion takes over. So that phase of initial very fast expansion is called inflation. So when you see inflationary scenarios, that's what it means. And that is required in order to explain certain distributions of galaxies in our universe. Yeah.
Yes, ma'am.
What is alpha energy? Alpha particle or alpha particle? I don't know what is alpha energy. Alpha particle I have heard of. Huh? Yeah. So those are particles. So alpha is nothing but an alpha nucleus. Helium nucleus is called alpha. Okay, so it's a particle. So the thing is that you can see that helium, even electronically, is a noble gas, right? Noble gas means it has a closed shell, so it's very tightly bound. So helium nucleus is also just like the helium atom is very tightly bound. It's like a closed shell. So when you have weak interactions and okay, you should go back to your periodic table. If you look at carbon has 6 protons, 6 neutrons, 6C12, right? Helium 2 He4, 2 protons, 2 neutrons. When you go to iron, for example, it's 2656. So there's 26 protons, 30 neutrons. Why are there more neutrons than protons? Can anyone tell me? If you go to heavier nuclei, there are many more neutrons than protons. No, because the protons no one asks, how can I put 2 protons together? They repel, right? So in fact, even helium itself should have been a problem. But that's why they're called strong interactions. The strong interactions are so strong, they overcome the repulsion, the electromagnetic repulsion of 2 protons. And so you stuff in the 2 neutrons. That is why you don't have only protons bound state. The moment you have a proton plus neutron gives you deuteron, right? You have to have a neutron. You cannot put 2 protons together and form a bound state, right? So as you go to heavier and heavier nuclei, you have more and more protons, which are more and more repulsive, mutually repulsive. So you have to stuff in more and more neutrons to overcome this. And that's why you have, if you look at heavier elements, if you look at uranium, or as I said, even iron itself, you have more neutrons than protons. And if you keep on stuffing more and more neutrons, and at some point they'll become unstable. So the neutron can decay. As I said, neutron can give you an electron neutrino. So this electron is not emitted from the atom. It is emitted from the nucleus. This is called beta decay. So neutron can go to proton and give you electron. This is provided the energetics allows it. So just like an electron or positron can come out, photons can also come out. You excite the nucleus, it de-excites, emits a photon. That photon will have, it's called gamma radiation. Why? Because the energy is in the MeV as opposed to 13.6 electron volts of the atom, right? So that is why that energy of photon is coming from the nucleus and not coming from the atom. That's how you know this, okay? And finally, the other thing that you can have is an entire unit of 2 protons and 2 neutrons can come out from the nucleus. That is called an alpha particle. So that's why you have alpha, beta, gamma rays, and together they're called radioactivity. Right? Okay. So you have to take this and ask.
Seeing the dark matter doesn't have any particles.
We don't know.
No, as per the which upon last presentation which you have it here. So dark matter doesn't have the particles, but dark energy is 72% is there. So how that energy is coming there? So what are all the things? Maybe just I have a little bit understood them.
We have no understanding, sir. No one knows. I don't know anymore. No one knows. We know the measurements have told you that this matter exists. Whether this matter is in particle form, wave form, neither particle nor wave, we have no idea. We have been desperately searching now for the last, this was discovered in the 1930s. So, so we have only got better and better data. We know that it is definitely there. Now we have different experiments looking at different regions of the space, and we have established dark matter exists. But beyond that, we don't know what it is. And dark energy, you can forget it.
By use of the 8-volt forces, gravitation, EMF, nuclei. Can we explain the dark energy matter and also the cosmic position system? As you explained, global position system, madam. But what I'm asking you, the cosmic position system, by the use of the four forces, gravitation, fusion,
Okay, let me pass this question as how have we seen dark matter? We have seen dark matter through its gravitational interaction. Because we have seen the size of this interaction, we have made an estimate of the mass, which gives you the energy actually. That's how we know how much energy budget is there from the dark matter. But whether this mass is divided into particles of units of this much mass or this much mass, we have no idea. So we have observed it through gravity. We have not observed it through electromagnetism. So we know that it is not charged. Weak interactions and strong interactions are extremely short-ranged. So unless you go to that galaxy, we will not see it. Okay, because on Earth, everything is dominated by visible light, visible radiation, visible matter, right? So even though there is dark matter on Earth, there is dark matter in the sun, but we will not be able to see it because it's very weakly interacting, right? So we have to look for it in other clever ways. We have not succeeded. So we don't even know whether it has a particle nature or not. But there are hundreds of theories to explain darkness. There are also some questions, open questions within what I call the standard model of particle physics. Are strong interactions, weak interactions, are mediators. There are some open questions there also. So what people are trying to do is to try to do two-in-one kind of physics. You want to explain those open questions in the standard physics that you know, which will also simultaneously give you some predictions for the dark matter. Then you go and look in the experiment and look for it, and no one has succeeded so far. But definitely it experiences gravity. There is no need at present to add any extra force. People have looked for a fifth force. If you go to Wikipedia and search for fifth force, you will find a series of experiments. They're all null results. But this is what physics is. You have to look. No, you cannot simply say. You have to look, and if you don't find, then you can say, yes, we have not found a fifth force. There are only four forces. Okay. Yeah.
Some friends are saying that multiple universes are existing. This idea is pseudospace.
Okay, so I talked about mathematics being the language of physics, right? You write. By the time you go to college, you start writing physics in all equation form. So when you write certain mathematical models, you will get solutions which, if you are at a very junior class, you will call unphysical and throw it away. But which, if you go to higher and higher levels, you say maybe maybe there's another universe where this is true. So the notion of multiverse, parallel universes, wormholes, all these things do have a place, not in the particle physics that I talked about, but in string models of the universe, they are definitely there. But how you will actually physically confirm their existence is a very different question. In order to actually confirm, you have to go to an energy scale, which today we cannot go to. So if I'm very cautious and this thing, or if I want to be very pragmatic, I say, this is my universe. Let me, and even that I don't understand fully, right? I understand 4% of this universe. But who prevents you from looking at parallel universes? Certainly, it is very, very attractive for people who write science fiction, right? But doesn't mean it is science fiction. Okay, it's just that, I mean, Gamow, for example, George Gamow has this beautiful book on what if the velocity of light were 15 kilometers an hour. I mean, how you would see people walking towards you, how you would experience relativity in day-to-day life, right? It's amazing. So you can convert that to, the same kind of ideas. Need not be fiction, but it's just very hard for us to see it in today's world.
What's the speed of the sound, madam? Speed of the sound.
Speed of sound is different in different matter, right? It's about 330 meters per second in air. But in fact, in water, it is much higher, right? It depends on the density of the medium. It's different. It's not like light. No, light doesn't depend on the medium for transmission. So that is different. Are there questions from the back?
Yes.
Yes, please ask, because the mic is not reaching you, so it will be very unfair. I'll just pass it down to the person's side. You can pass it. Yeah. Okay, sorry. His capture cross section was very high. Okay.
Everything on the quantum gravity.
Okay. So clearly, this is a question outside the syllabus. So the thing is that Okay. Theory of everything also to be very, very simplistic, I told you that gravity is not part of the standard model of particle physics. If you want to include gravity, today there is no quantum theory of gravity that has been verified in the form that electromagnetism or weak interactions has been verified. Okay. So if you want to include gravity, you have to go to different models of particles. Okay. That will be called the theory of everything. And at that time, you will find a theory of quantum gravity. I will leave it at that point. Okay. No, I think we will go strictly in chronological order. Otherwise, people at the back won't. It will come back to you. It will come back to you. By the way, the talk is officially over. Those who want to leave can leave, and those who want to ask questions can stay. I mean,
Quick questions.
please ask one.
So, so are you ruling out concepts like Panchabhutam and Trigunas and Ashtachakras, all these things? Because they also try to define these are the stuff that universe is made of. So I'm saying all that is like hot air. That's my first question.
No, stop. I have to answer one. If you ask three, I won't remember. I'm old. Okay, you have to ask one by one. So hot air, I can tell you what hot air is in my theory. Okay. So what Panchabhutas are, I have no idea. I have not studied them. Okay. So
Second question is, see, there is something called space
Uh.
without any matter.
Uh.
So everything that you describe does not describe what space itself, the construct of the space itself is made of, right?
that's a very nice question, by the way. Since I didn't talk about gravity and everyone is asking about gravity. So what gravity does, what Einstein's theory or general theory of relativity does, is to tell you that
She needs a mic.
no, I think I'm shouting enough if you can hear me. So the Einstein's theory tells you that now what you called, for instance, matter and radiation as being equivalent, now you're talking about gravity and space-time as being kind of, because you know that gravity curves the space around you because it bends things, because mass is attractive, so it bends. So if I'm very massive, it bends the space-time around me. I can start with the curved space-time and throw away the matter, right? The curved spacetime could have been there because of some initial mass, but I don't need to put in the mass in order to study the curved spacetime. So you can study pure spacetime theories without masses, and that's an equally good theory of gravity. So they're completely equivalent. Instead of the mass, I can put in the curvature in the spacetime, and I can simply compute. Okay, your last question. No, you have to give it to here, this person in the blue striped shirt.
Can you get the mic?
Yeah. Oh, sorry, you were the one who asked. I'm sorry. Okay.
Result, what were the experiments that we done for discovering dark matters?
Here, I showed you one. I showed you the velocity. Here, these are the ones.
For this one.
This one. This is an experiment, right, with data points.
Okay. Okay.
Yeah, this is one example. You can look up something called gravitational lensing. That will also tell you.
And the second question is that, I mean, based on the astrology. So there are planet astrology is based on the planet movements, and based on the planet movements, they'll be deciding and giving some opinions about the person's life. Do you believe about it, or what is your opinion?
Do you want my opinion, or do you ask me whether I believe about it? I have no opinion on it. I don't. You know more than I do about astrology. I have never read it in my life. And I mean, obviously, that is.
Yeah, 3 more questions. Okay, we go.
Okay, 1, 2, 3. Okay. Oh, you're not the 3 that we pointed to. You didn't raise your hand. Okay, 4. Okay. Please use the mic. Please use the mic. See, everyone should hear your question. Otherwise, there's no point in my answering.
Can we please speak about quantum tunneling?
Okay. Okay. Yeah, you guys are asking me only questions beyond the syllabus. That means either you didn't understand my talk at all or you didn't like my talk. Now I have to figure out which one. Okay. Okay. Fine. You have to give me back the mic or I have to shout. Okay. So here is an atom. Doesn't matter what atom it is, right? Now in this atom, there are electrons and there is a nucleus, right? So now let's assume this is a hydrogen atom and this is only one electron here. Thank you. There's only one electron here. I have to stop shouting now. Yeah. And when I want to move this electron out, I have to give it 13.6 electron volts. Right? Suppose I give it 13.5 electron volts or give it 13.4 electron volts. Right? It's less than what is required, right? Now the thing is that in quantum mechanics, there is no full yes, no answer. Quantum mechanics tells you probability that something will happen. Okay. So probability that the electron will actually be able to escape from the atom with 13.5 electron volts is not zero. This is very, very small, but it is not zero. So this is called quantum tunneling. So even though something is not allowed exactly classically, it can still happen quantum mechanically. Okay. So think of it as physically like a barrier. I'm sitting, actually that is the model. I'm sitting in a potential well. The well has boundaries. It has a barrier. And I am the electron, and I want to go outside the barrier. Now, if my energy is not the height of the barrier, then classically I can never come out. But if it is close enough, there is a non-zero exponentially falling probability that I will actually tunnel outside. This is the meaning of tunneling. Unless the potential height is infinity. If the potential height is infinity, so the well I'm sitting in has infinite height boundaries, in which case even quantum mechanically I can never tunnel outside. But provided the barrier height is finite, I can always go outside. There will be a non-zero probability of finding it outside. This is in fact how two protons, this is what gamma, by the way, there is, I saw a book. George Gamma was the first one. So you have to make first and that also happens. So you have to bring them close enough together, and then suddenly they'll realize, now we can fuse and become proton, neutron, we can, become deuteron and then release energy, we become exothermic. All that happens. So this is the meaning of quantum mechanical tunneling. Thank you, sir. When Dr. Murugan tells me something is nice, then I feel very good about it. Okay. Huh? See, I can stay here. I have no problem.
Okay, let's have a limit. We'll have 3 more questions.
Although the lady at the back asked a question. Huh? Okay, one lady at the back also.
Kind of within the syllabus. Side question, the E is equal to mc square equation.
Yeah, keep going with your question.
Yeah, actually, you referred to like Minkowski's equation and it had a relation of the minus T1, minus T2 other thing. So I didn't quite get it how it came into this equation as like px square. How did it become minus sign?
Okay, so I said that, minus sign, no, minus sign. Minkowski said there is such a space time. Yeah.
Related with this equation and px square, then it became.
So what we say is that this is just to do with linear algebra, right? You have all studied linear algebra. Oh, Mike, sorry.
You said you can later share a PDF like through which
anyone can take this PDF. Yeah. Or I put my.
It's also will be in the YouTube. You can watch it.
Okay. So you can tell me what all mistakes are there also. So if you remember, so as I said, this is linear algebra, right? I have a space, and in 3-dimensional space, I know what is my invariant. My invariant is the distance, which is x2 minus x1. Let me just call it x squared plus y squared plus z squared. Is an invariant, right? In Minkowski space, it is dt squared minus x squared minus y squared minus z squared, or the other way around, x squared plus y squared plus z squared minus t squared, whichever way. So I can think of a vector in 4 dimensions, which should have 4 components. It's called a 4 vector, which has components time x, y, z. And the invariant will be time squared minus x squared minus y squared minus z squared. Now you can see that I have a vector here. I have a 4 vector here. The components are E, PXC, PYC, PZC. And the same relationship, E squared minus, please let me drop the C squared, E squared minus PX squared minus PY squared minus PZ squared is an invariant if it is there in space. What is the invariant relationship between the vectors which have components E, P is the mass of that polygon. So that is how the mass center. It's a geometric quantity. I can write any 4 vectors in 4-dimensional space time. the four vector which contains time and space, the invariant distance as the corresponding invariant, and the four vector which has energy and momentum as its components. There are four components here. E, Px, Py, Pz will have mass space squared as the invariant corresponding to it. So now mass is a geometric quantity. Is that invariant which the four vector satisfies in this four-dimensional Minkowski space?
Okay, last two questions. So,
that lady here, is it okay, or this gentleman behind, or I think?
no, I can see so many hands.
Okay, fine. So I think four people start walking to the front, so I can share the mic with you, and then only those four should ask questions. Okay.
A question from out of syllabus. There is a famous question. So are we the only life forms in this? What is your opinion?
See, physics is not about beliefs. So let me say this. We have to be very clear. See, I think it's you have opinions about anything. It has to be a theorem which I should be able to go and actually determine in the lab. Okay, that I am a life form, I cannot deny. What is a life form? I don't know. This very famous question is there, no? A candle can be born by giving it a flame. It can die when the flame runs out or when the candle wax. Is it a living thing? I don't know, right? How do you define life? I don't know. What are the life forms on Earth? We don't know all the life forms on Earth because we may not have seen all of them. So when you ask a question like this, you make sure that it actually has an answer which is going to meaningfully add to the body of the. There are so many nice questions you can ask within the syllabus, right? I mean, so I'm serious about this. See, today's world, okay, there are many things people are talking about. What is the science in the Vedas? What is astrology? I am not qualified to answer any of these things. You must ask a teacher what she knows. It helps the ego of the teacher when I can actually answer the questions. Okay. Good. So you should tell me the answer, right? After this talk, you please wait and answer the questions for me. Come, next person, please come.
Thank you, ma'am.
Sure, welcome. By the way, I mean, I'm not criticizing anybody. Let's stop this.
The gravitation force between the two masses you say that the universe gravitational force you are equal to G in your one M2 by R squared.
Keep going, ask your question.
Yeah. Why instead of R, he said R. Even the R also decreasing when we expand the two masses. If the distance is rising, the definitive force also decreasing. Why the formula instead of R square? Is there any reason behind that? Even Coulomb's law is the same principle. Q1, Q2 by R square.
Yeah. So, first of all, in physics, there is no why, because you have to explain what our universe looks like. I did not make this universe. I have to only discover. So we can ask how. So how is masses interact? They interact about it. Okay. So I cannot tell you that it has to be 1 by R squared. It is observed to be 1 by R squared. Is it different from 1 by R squared, for example, if it is an infinite force? If I multiply this by, say, something which is exponential minus, then the exponential will fall very fast. It will go to 0 much before infinity. That becomes a finite range force. Now, there's a very deep connection between the range of a force and the mass of the mediator particle. Say, finite range force. This reflects the fact that the photon particle is massless. Okay, this relationship I cannot show you easily. We will have a finite range force. What a finite range force. Same with gravity. Associated particle which mediates gravity is called a graviton. I did not talk about it out of syllabus, but the graviton is also a massless particle. It's a spin particle. Photon is spin one particle. It's also, but the thing is that if so 1 by R squared, reflect the mass of non-zero mass. So people have actually, if you go and ask, constant array bound on the, it's very small. mass of the photon experimentally is 0. They will tell you it's 10 to the power minus 40 something. I don't remember what the current thing is. So these laws reflect certain symmetries. The exact masslessness of the photon actually becomes the symmetry under which quantum electrodynamics is written. Okay, so there are relationships, but these are all how. The observation drives for you what Lagrangian choice you will make.
It's a universal truth.
This is not universal truth. My universe has this. Okay, one last question, if there is any. Yes, sir. Yes.
So we talked about 4 fundamental forces of nature. So I have read somewhere there's this talk about this one force thing, like universal force, where these 4 things are integrated, or these 4 things are manifestations of a single force. And I have read that gravity, however, is an outlier in that. It cannot be integrated. But the other 3 forms, like electromagnetism and strong and weak forces, they could somehow be integrated. I don't know the exact details of that. So is it true, like electromagnetic force and strong and weak forces are different manifestations, a single kind of force?
Your question is very interesting, but it requires a 1-hour lecture. Let me see what I can do in 3 minutes. Okay. So I said that these are diagrams which indicate how particles interact. So there is a mediator force. Now, if this mediator force is a photon, due to a photon, then at this vertex, the strength of this, what I would call an electron current interacting with the photon, is the proportional to the charge of the electron. So if I put a proton here, it will be proportional to the charge of the proton. If I put a U-quark, it will be proportional to the charge of the. And if I put another photon, it will not interact because its charge is 0, right? So this vertex factor, or the strength of the interaction, is called E, which is the electron charge. And all particles have either plus minus E or units of something E. So I can say that I can write a coupling constant, which tells you what is the strength of electromagnetic interactions. It is called E squared by 4 pi. This is called the fine structure constant. It's 1 by 137, which is a very famous number. I think many of you have calculated 1 by 137. It's about 10 to the power minus 2. So this is the strength of electromagnetic interactions. On the same scale, if this was actually a gluon, I would put, instead of E, I would put something called G as the coupling constant, and I can compute something called G squared by 4 pi instead of E squared by 4 pi, and that will come out to be of order 1. And I can compute the same thing for weak interactions that will come out to be of order 10 to the power minus 5. Some units, doesn't matter. So weak is weaker because it's 10 to the power minus 5 compared to 10 to the power minus 2 of electromagnetism compared to 1 of strong interactions. Okay. Now, the complicated thing, all this I can say in 2 minutes. Now, in the 3rd minute, I have to tell you that these constants are not constants. Heisenberg uncertainty principle tells you that the scale of an object tells you the energy associated with that object. So if I probe deeper and deeper with higher and higher energies, these constants start to change. So all these so-called constants, even the fine structure constant, is actually changing. It's called running. It runs with the scale, energy scale of process. And it turns out that electrodynamics, the constant increases, and in weak interactions, the scale decreases and strong. And if you go to high enough energy at some point, all these constants meet in one point. That is what you call unification of all the forces. So the forces don't unify. The strengths of these forces unify at some very high energy, which is 10 power 15 times the mass of the proton, which will never reach in the lab. But theoretically, they will unify. Okay. So this is the meaning. And gravity still remains outside. But gravity will only unify on the Planck scale, which is another 15 orders of magnitude more than that scale. Okay? So I don't know if this explanation satisfied anybody. Sorry, my very technical explanation. Okay, so I think at the bottom line, there are things in science to which precise questions can be asked, to which we do not know the answers. And I think research or advances in science happen when the questions are put as precisely as possible, so that the answers are also not very vague, but very precise, very specific. You might not be able to get yes, no answers in physics, but the more precisely you frame the question, the more precisely you get the answer. And one thing I want to give one little bhashan in the end, because I heard a lot of your questions. I think today, in somehow in this society, we are in a state of flux. We want to, we want to somehow say we do very good Indian science. But you see, the names that I have taken are all not Indian scientists. Okay, science is something which is the most collaborative thing in the universe. Okay, we literally, as Newton said, we stand on the shoulders of other giants, and therefore we see further. And this is very true in today's universe. I mean, all of you have cell phones. How many of you have an Indian cell phone? How many of you have not only Indian manufactured, but Indian designed cell phone? So we have to get there. We have to invest our science into some technology which we do ourselves. Not 2 kilometers from us or maybe 5 kilometers from us is an institute where the entrance exam is a theory entrance exam for an engineering course, right? At some point, we have to understand that to understand this universe and to improve our technology, we have to do things with our hands. We are not, I mean, I am a theorist, but doesn't mean that I'm looking down on experimentalists. In this country, we need people who get recognition for working with their hands. Okay, if you go and ask who are the engineers, because when you have a plumbing problem, you call a plumber, you don't call a civil engineer, right? It just shows that we don't think of engineers actually as being useful to our society today. We have to somehow change that feeling. All of you who want to do engineering, great thing, but continue doing engineering. Use your hands, don't become managers. And somehow that flow which happens in the Western countries, where 90% of people from research actually go over into doing things with their hands, experimental sciences, into industry, factories, engineering. That flow I don't see in India. And this is what is actually holding back our economy today. So I think if you seriously are interested, I am very invested in this country. That's why I live here. And I think that this is something that you people should think about. Why are we importing goods? Because we don't make them ourselves. Why don't we make them ourselves? Because that atmosphere of freely doing research in colleges and universities is not there anymore. It was there when I was in college. And why did we lose it? Why are we not being able to get that feeling of freedom, of exploring, of our being able to take our curiosity to our university labs and talk to teachers, and we should get there. And I think that is something our senior people should seriously, introspect about. Otherwise, I think it will be very hard to keep up with. We'll always be doing derivative science. We'll always be importing their goods, and even our research labs. We import the equipment, and all of you have seen in universities. Oh, we have this marvelous equipment which costs 10 crores. But then make it yourself, because in that there is learning, right? There is understanding. There is innovation, and that is how there is progress. So this is, if you really want my personal opinion, this is my personal opinion. Okay, thank you.
So we have
Oh,
so we have Sri basket.
thank you. Thank you. But I found your collection so impressive, actually. Very nice. Thanks. Thank you so much. Yeah. By the way, I strongly suggest you people look at the books in this library. I find this wonderful collection over here. I didn't know myself, actually. I'm certainly coming back to read some more. So thank you, everybody, again. So I will sit in the corner, and anyone who wants can approach me.
So before closing, just a few announcements. If you are not aware, this library has recently opened the membership also. Earlier it was only a reference library. Recently it is open for public. You can with